I'm Tim Swanson from Cisco Systems, and John Joyce is as well from Cisco, and we did a talk earlier on DNS. So this talk will be more on actually the NSM interdomain scenario. We'll do a functional walkthrough, some use cases, and we'll do a very quick demo. We have a lot of slides, so we're going to try and fly through this a little bit. So NSM interdomain. So if we talk about NSM interdomain, we have to really kind of understand in the implications. We have to understand really the kind of the sort of primitives that NSM gives you. NSM. This is a quick recap on the connection setup that happens in a normal Kubernetes multi-node environment. The connection setup is done via a network service client, which is represented as a workload pod here in this picture, initiating a connection request, a network service request to its local NS manager, network service manager. And that network service manager is the thing that chooses what NSE will be serving or directly connected to that workload pod, that exact workload network service client. And the way it does that is it uses a network service registry to find all of the NSEs for this network service. And then when it decides, oh, that's a NSE on another node, it will contact a peer or basically forward the network service request to a peer. So the peer in this picture is another network service manager that is on node 2. And that's the same node where the network service endpoint is. And then the network service endpoint gets the request, fills in its connection details, and then responds. And network service managers on both nodes issue some corresponding calls to the forwarding layer, and that causes this vWire to get set up between the nodes. So if we think of, if we go to the interdomain scope, it's exactly the same pattern, the same from the client's point of view and the NSE's point of view. It's identical. They're interacting with their node local network service manager. The difference falls into what happens inside the network service manager. And the network service manager, when it's deciding which NSEs it's connecting to, it needs to be able to have a view of all the NSEs for the network service. And for interdomain scenarios, it's either configured explicitly to access a proxy network service manager, or the actual network service request format is indicating that it should try to go through the proxy. And so in the role of the proxy is to act as a peer manager to the cluster local network service managers. So this is the thing that knows which cloud environment it's in, which cluster, the cluster details, and has the view of, is able to provide the view of the network service managers in its cluster, how they look to the other clusters or other outside world. So it's got to have in the reference implementation, what it's doing is looking for, it's basically translating the identifier for the local network service managers to the Kubernetes node objects external IPs for that node, and the corresponding port that network service manager is listening on. So we really see just a fundamental identical pattern from the actual control plane messages, but there's a proxy involved that's tweaking or mutating what's in the actual messages to reflect reachability information across cluster or cloud boundaries. So the very similar, the concept of the data plane is when I introduce that, what we're introducing is the actual semantics between the cross connect API that is local to the actual individual nodes. And so the NSM forwarder is implementing the cross connect API, and it's on each of the nodes, and then in the context where the network service manager knows how to communicate with it to provide the data plane to create the cross connect between the actual network service client workloads and the network service endpoints. So when we go to the higher level, the proxy, the interdomain scenario, the data plane model is identical. The delta here is more on what the content of the actual message in the cross connect APIs to the forwarder, and that's set up. The connection details are set up by like a layered approach where the actual each individual hop in this control plane message can provide additional connection semantics that can be consumed by the other hops and result in a data plane that's implementing a cross connect between the forwarders, as well as between IP information, or in the previous talk we showed DNS context information, but additional L3 or higher sort of connection information that is carried out by the forwarder or the NSEs themselves. And concerning the cross connect, these forwarders, when they are in their hop in the control plane message interaction, they are expressing the capability that they have to the network service managers, and the network service managers is choosing a network service connection type or a mechanism type for the connection that both of the forwarders involved can support, and the actual parameters are set up by the serving side forwarder. So like, for example, for VXLAN, that's like choosing the VNI, right? So the VNI is set up by the serving side forwarder, and then that's communicated back through the control plane messages to the client side forwarder, and that client side forwarder will then use the destination IP that has been set up for this forwarder. So this has to have external reachability. So the forwarder has to be able to some combination of the deployment of the proxy, and the forwarder has to be able to express that externally reachable IP for the forwarder, and then the VNI is expressed as well is chosen by the forwarder itself and passed to the actual the client side forwarder. So then the connection parameters are in sync between the forwarder side on the client versus the server side. So that's a quick explanation of the data plane. How do NSEs get known in this system? So there's a concept that the NSM community has created called the floating interdomain or floating domain NSE registry. So what that really means is it boils down to just this idea that there's a network service registry that exists for a domain that is outside of, not tied to the cluster boundary. So you could implement this in a variety of ways, but the primary example is to have a specific network service registry that exists somewhere that's reachable by both of these clusters control plane elements, and have any network service endpoint registrations will get proxied to this floating domain network service registry. And the view of the endpoint data in these in this floating domain network service registry will be like an external view of the NSE. So the actual reachability of the NSE is going to be identified as using the external reachability for the individual network service manager that NSE is registered locally with. So in this example, the NSE is registering to, on node 2 is registering to NS manager 2, and then that is forwarding the registration request to the proxy on cluster. It should be cluster 2, but it says on the right. Excuse me. And that proxy is going to mutate the registration to indicate the external reachability for NS Manager 2, and then forward that registration onto the floating domain NSR. So this floating domain NSR now has the NSE in node 2, cluster 2, node 2, and the external reachability for the external contact information for the network service manager in that same node. So in the connection sequence, I'm going to walk through a sequence diagram. It's going to be complicated, but this is also meant for being able to view offline. So we are in our node cluster 1 on the left. We have a network service client that is going to issue a network service request, and it's going to use a format that indicates that it's requesting a network service that belongs to a floating domain, and that floating domain is called nsr.foo.com, and somehow the DNS for resolving nsr.foo.com in each of these clusters has been pre-set up. That could be like a Route 53 zone in AWS, and you have, these are 2 different VPCs with 2 different EKS clusters, for example, and you've attached that zone to your VPCs. So the client indicates its network service request with the NSR domain name in this format, and the network service manager is going to do a find NSE call to determine which NSEs it can connect to. The NSR is going to notice that that's an actual not in its local domain, and so it's going to call the proxy that is local to the cluster 1, and that proxy is going to resolve the domain name and call the find network service API in this floating domain NSR. And when it gets the response, it's going to pass that all the way back to the network service manager that initiated the find of the NSEs. And this network service manager is going to choose an NSE, and that's going to be the cluster 2 NSE. So it's going to call its proxy network service manager so it can reach the actual other clusters NS network service manager, and it also calls it so that the proxy will indicate how to get back to this local cluster 1 network service manager. This proxy on cluster 1 is going to directly invoke forward the network service request after mutating it with the cluster 1's information. It's going to call cluster 2's network service manager directly, and that's so that's going to actually be the thing that locally binds with the actual NSE. So the NSE is going to consume the network service request, fill in its connection context information, and then set up its local resources. And then it's going to reply. And when it replies, this whole chain unwinds, and the network service manager in node 2 is going to invoke the forwarder with the connection details. That's going to fill in its connection context info, and the response back to cluster 1's proxy will come back through to the cluster 1 initiating network service manager, and then that network service manager will invoke the corresponding connection cross connect forwarder API with all of this connection detail intact. And so then these two forwarders will now have the same exact connection properties, and will operate on them to create the tunnel between the nodes in the two clusters, and concurrently they'll create the client connections to the actual, the local connections to the actual workloads, the NSE's namespace in the pod, as well as the client side namespace. So then at that point, the full cross connect is up, and the client now has a network service manager interface and a network service mesh interface and all the accompanying normal stuff. So what are the use cases for something like that? The first one we call is a private layer 3 network. So there's an idea that we could basically use this to create two sides of a L3 VPN that between in specific workloads and in specific clusters. So this use case would be really relevant for, relevant for database replication or sharding. So where you have geographical reasons to have either different clouds, for blast radius or mergers and acquisitions, something like that. So we have a talk with the Vitesse project on this exact scenario, where instead of just the raw database, here we have Vitesse pods, and Vitesse is a CNCF project that makes sharding and replication very cloud native, and with the proxy kind of model, and gives actually complements this NSM VL3 scenario very well. So I have a reference to that later on. But the idea is that each of these workloads just adds their annotation for a local local identifier for the service, and then they get attached to a private network that's interconnected between clouds. So this is, we have this VL3 NSE, and that handles finding the other NSEs that are under VL3 NSEs in other clouds or clusters, and it uses a common floating registry, and for that VL3 network, and then it will create the connection requests, and NSM will carry out the actual forwarding plane. So another use case would be if you have a specific network function cluster. So say you have a cluster, you want to have, this is kind of like the transit VPC model but it's adapted for specific workloads connecting to those network functions in that separate cluster or VPC. So this would be like if you have an administrative boundary between where your NSEs, you don't want them to be actually deployed into an environment where your customers are, or your internal organizational customers are, and maybe for security reasons, maybe you have some specific network function runtime environment dependencies that you want to only provide, you want to guarantee that your network functions only use like SRILV or SmartNICs, or you have some very specific things to tune your network function like CPU pinning or huge pages. This would be this would be a model that you would potentially want to use. So your client pods are just getting cross-connected with with a generic forwarder, and you have a corresponding forwarder connection into your actual network functions. So maybe like you have a slew of nodes that have a lot of different capabilities that you want your NSEs to land on specific nodes with specific capabilities, or maybe compliance requirements for security, or that you have in your network function operations criteria. So this would be a reason to do interdomain, right? Your clients are on a different cluster as your actual network functions. And then the other use case is probably the more obvious one, was like something that would maybe provide a direct connection to appliances. I think somebody had a talk about this earlier, but the idea is that your network service endpoint is really not, it's not necessarily actually in the data path. It's more carrying out the connection context and mechanism details. It's putting those into the message in the control plane messages for the connection setup, so that the network service mesh forwarder directly connects to a network function, and so that there's that's sort of like a thin layer network service endpoint that is purely speaking NSM, but also understands maybe some SDN on the back end, or understands the topology between a network service mesh forwarder and the network functions. Okay, John, do you want to take it?
Yeah, sure. So we're running a little short on time. We want to get to the demo, so I'll go through this quickly. It actually builds quite a bit on our earlier presentation, where we talked about the need for some control services, an NSE API that we use to try to help provide those services. We're going to just show here two ways we use that API and two of the services that we require for our particular layout leading up to the demo. So if you're going to go through a little bit. So the first one here is that we need, and this was alluded to even some of the very early talks, is we need some kind of IPAM. We need, when we're deploying these services, we need some kind of, we're going to have a network between the NSEs. We're going to have that virtual L3 network that Tim referred to. And so we have to provide some addressing information to make that happen. So what we do in this particular case is we configure some IPAM pools into a server. In our case, that server is centralized, but you could imagine distributed architectures. And then when the NSEs come up, they have a way to call into that server and request their pools. So that server is able to manage the pools and provide the addressing that provides us that layer 3 network to interconnect those NSEs. So that's one control service that we use. If you keep going, let's see. So we're just laying out the different, how the flow goes from the bar requesting or foo requesting a service to the NSE. The NSE will assign the endpoints, and you can see here we've blown out the topology of how, based on the IPAM services, how each particular application gets its addressing within the overall layer 3 scheme. In the interest of time, I'll let you look at the addressing offline and not try to go through one by one. Tim, if you want to move on. So we talked about this one quite a bit in the first talk. So again, I'm going to try to go through it quickly for those that didn't see it, but the earlier talk goes into it quite a bit more detail. But we also have the need to provide these applications, foo and bar, in this particular case, some DNS services. They have to be able to reach each other. They need to know to reach each other via the NSM networking, that layer 3 network that we set up, versus maybe a traditional CNI network. So that's the need, and this is sort of how we use that control service to handle the population.
Sorry about that.
So so Tim's jumping me along because he took up all my time. So
I accidentally hit the button, like held it down.
okay. So here's
So this is
yeah. So just quickly to wrap up. Again, we don't have much time. This is the API. It's a very simple API right now. We could add additional entry points and additional details, and it is available. That repo is a public repo. But it hasn't been, we haven't attempted to push this up to master yet, or for community to comment on. So Tim, why don't you jump on to the demo?
Sure. So like I mentioned, there's another talk for actually demonstrating this interdomain work for the VL3 integrated with Vitesse, and so that has more of the user view. So that's how more on the use case for why and what the implications are. But for interdomain, I have a tough time really breaking down what we wanted to show in the demo. So I really wanted to focus on how the connection details are set up between individual clusters, and what sort of things happen inside there. So this demo is going to show some Jaeger traces on two clusters, and showing how the mechanisms for VXLAN get set up. So this is in a handler for, or that side was the request side. So it was indicating like the information that it was seeing as a response from this cluster. So this is cluster 2, and this cluster has a, this is the handler that actually sets up the mechanism properties for chose the VNI. So this received the peer clusters information. So that control plane, kind 2 control plane is the identifier, and that 172.17.03 address is the external reachable node IP for that that other cluster's NS manager. So this is where the VNI is set up, and it's shoved into the mechanism parameters in the actual network service request response. So this is the response that's gotten filled in by this local by this cluster's request handler for remote connections. So then after this happens, that's going to go to the data plane, and in this case it's a VPP data plane. So this is the VPP forwarder. This is a tool created by Andre Fabry in the Legato project to view multiple VPP instances. So this is a VPP instance on the first cluster, so cluster the one that was actually the client of that connection we saw. And you can see in this output that there's actually 3 connect tunnels up between the clusters. So this is because there's 4 total network service endpoints in these deployments, 2 in each cluster. And so that from the point of view of this forwarder, there's only, so then that would be 3 connections across the tunnel. So each of these tunnels you can see is the first VPP calls it a destination and source, and the second one has the inverse, right, for the names. But this is all the VXLAN data that's actually this is the actual VXLAN tunnel that's brought up as a result of the connection setup parameters in the control plane messages. So that's pretty much it for the demo. I know that I could spend an hour on that demo and give a lot more detail, but that was the gist of showing what happens during the control plane. For more references, the network service mesh GitHub has an interdomain documentation with some similar pictures to what we showed in this slide deck. I'll share the slide deck as well. And then here's our the NSE that has that VL3 NSE with the network service control services API definition, and for the reference for replication and sharding, I have a pointer to PlanetScale and the Vitesse project, and there's some more talks on using network service mesh in an interdomain manner for a lot of different solutions, but mainly we have that's our executive keynote is going to be a part of that, and then we have some information on the Vitesse talks for related ideas and exactly this network service mesh VL3 integration. Okay, thank you. Sorry, Ed, for going over.
So thank you very
much. Doing great.
Yeah, and thank you very much. So we do have a question, but we may want to take the question to Slack from Abid Ahmed. So Abid, if you can join Slack, then we'd be happy to have someone help.
On Slack.